You guys, here's your very last video installment of Chemistry 111 that we'll be covering this semester, which is the very beginning of Chapter 11. Chapter 11 is about intermolecular forces in liquids and solids. So we did gases in Chapter 5, remember, and gases were really far apart in their container, if you will. So when we drew a container of a gas, we would see, we draw it like this and we have the gases really far apart. Now, what makes liquids and solids different, one of the major things is that they're much closer together. And since they're much closer together, their interactions are greater. And what we're going to be talking about are those interactions right now. They're called intermolecular forces, and we'll call them IMFs. So that was a really pretty picture, I always thought, of all this ice and everything. And I put it into black and white so we can analyze it a little bit. But in this picture, you see ice and you see water and you see clouds and all these different forms of our favorite substance, water. So we'll be looking at some different definitions here. And a definition that we look at in liquids and solids is a phase. It actually can be in gases too, because there's a gaseous phase in here. But a phase is a homogeneous part of a system in contact with other parts of the system, but separated from them by a well-defined boundary. And the boundary you can see just to draw along here. There's a boundary between the solid ice and the gas outside of it. And there's a boundary down here between solid ice and the liquid water down below it. So those are boundaries. And those are different phases of the system. So of course we have our solid phase, which is ice, liquid phase, which is water, and vapor phase, which is vapor. And I'm always thinking, well, what's a vapor? And vapor is a term that's used for substances that generally are liquids and solids at room temperature. So normally at room temperature and pressure, water would be a liquid. And then if there is any water vapor in the air due to evaporation, it's called a vapor and not a gas, which is kind of weird, but that's just basically your definition for what a vapor would be. So continuing on with what intermolecular forces are, they're attractive. They're attractive forces between molecules. And for those attractive forces to occur, normally those molecules must be close enough to each other. And that's why we're seeing that in this in this liquid and solid environment. Intramolecular forces are bonds, hold atoms together in a molecule, and those would be considered bonds. Intermolecular forces are between more than one molecule. Inter versus intra, as far as their kind of energetics, it takes 41 kilojoules to vaporize a mole of water, and that would be considered an intermolecular force. You're vaporizing, which means going from a liquid to a gas. But in order to break bonds, that's actually breaking the molecule apart into pieces, and that is quite a larger number, and that would be an intramolecular force. The measures of these intermolecular forces, though, which are between molecules, are things like boiling point. If you have a high boiling point, that means your intermolecular forces are strong. If you have a high melting point, that means your intermolecular forces are strong. So ice has a low boiling point compared to quartz. So melting point of water is 0 degrees Celsius, whereas quartz is a much stronger covalent network solid that has a much higher melting point, and that indicates its intermolecular forces are much greater. Heat of vaporization. Heat of vaporization is a parameter of a substance that tells you how much energy it takes to evaporate or vaporize something. And water's enthalpy, and remember these are enthalpies of vaporization, is about 40 kilojoules per mole. And alcohol is a bit lower. And you can tell that because you put alcohol on your skin and it evaporates right off very quickly, making your skin feel cold because that heat was taken from your body because you were being the surroundings. Heat of fusion and heat of sublimation, same idea. These are enthalpies, and those are for phase changes. Fusion means melting, and sublimation means going from a solid directly to a gas. So that's solid to a gas. So generally, these intermolecular forces are much weaker than intra. So the types of intermolecular forces that we'll be looking at here is dipole-dipole. A dipole-dipole force is between two polar molecules. So those polar molecules will align themselves positive to negative, and that's why they would stick together. I call that stickage. There will be more stickage in a polar subcompound than there would be in a nonpolar. Here was a kind of a neat little GIF I found. You know how I love GIFs of dissolving sugar in water. And you can see the sugar is being separated. This was a crystal structure here, and now it's being separated. And those sugar molecules are just kind of going away, and they're going into the water solution. Ion-dipole forces are forces between an ion and a polar molecule, like a dipole. So you would see these attractions between those things. One's normally a covalent compound, like this would be covalent, and then of course you'd have your ionic compound. And this is the dissolving of, say, salt in water. Now, between water and cations, there's different types of attractions versus strong versus weak. They're the same attraction because you have a partial negative here of the oxygen in water being attracted to the positives in the sodium and the magnesium. Now, this is going to be stronger, and it's stronger because of the higher charge on the magnesium ion. And sometimes it can be so strong that it can actually make water molecules align in a certain fashion. Octahedrally, this would be an octahedral arrangement. Here's another GIF I found for showing how sodium chloride dissolves in water. And sodium chloride would dissolve in water by the positive ends of the water interacting with the negative, and you can see the green is negative, and that water molecule drags it away. And then the negative is red, and it's interacting with the positive cations, which are purple. Continuing on with our intermolecular forces called dispersion forces are because all molecules have electrons. And since all molecules have electrons, those electrons can move. And since they move, because remember, they're not kind of stuck on the atoms themselves, they can move. And since they move at one moment, if I think of this as a molecule, I might have the electrons more on one side than the other. And since that's the case, you can have what's called a temporary dipole. And this temporary dipole then could be next to another one, because that negative is getting a bit closer to the one end of a molecule and makes the electrons in that molecule move away. Remember, negatives would repel each other, whereas positive and negative would attract. So if that happens, that means that that's an induced dipole. Now, an induced dipole can be induced by a cation, or it can be induced by another permanent dipole. So this might be something like a non-polar substance, and then this would be polar. And when you get them together, they don't like each other too much, but they can induce a behavior, and you might get some interactions, and those interactions would cause them to be soluble within each other. So this is called ion-induced dipole and dipole-induced dipole, and those are called dispersion forces. So dispersion forces are present in all substances. And when we use the word dispersion, and I ask you, well, what forces are present in this liquid? Dispersion is always actually going to be a choice, but that dispersion designation could be because of the fact that it's a pure liquid, and then you have two of the same liquid doing this type of thing, or dispersion forces could be something like this. Now, I like to give these their actual names, ion-induced dipole and dipole-induced dipole, if I'm going to describe those interactions. So this is what you might see, this induced dipole interacting with each other. And since these are all green, I would think this is like the same substance. This is like a bucket of a green molecule. And that molecule has electrons, and those electrons might shift around a little bit. And when they shift around, you get these temporary dipoles. Now the temporary dipoles are quite weak, and so that's why you would see them shifting around, and it probably would not be enough to keep it in the liquid phase unless it was cold. And if it was cold, then they might stay sticking a little bit more. Now dispersion forces again are kind of based upon this polarizability. Polarizability is the ease with which the electron distribution in the atom or molecule can be distorted. So the more electrons you have, the more polarizable it is. So the greater number of electrons, the more likely those electrons are going to move and cause that sort of stickage. And the more diffuse an electron cloud also affects that polarizability. So in this example in your table here, as you go down this grouping, you'll see that carbon tetraiodide, that's a much heavier substance. Iodine has a greater number of electrons than hydrogen. So since that's the case, you'll notice the melting point is actually quite high comparatively. So the more electrons you have, the more they can move, the more they can move, the more they can stick, and then you'll end up with a higher melting point or a higher heat of vaporization or whatever. Any one of those parameters that measured intermolecular forces would be affected. So again, dispersion forces increase with the molar mass, and that's because you have more electrons. So let's just take an example here. What types of intermolecular forces would exist between these molecules? Assuming a pure sample of hydrogen bromide, you would see it's polar, so it's dipole, dipole, and dispersion. If it's methane, it's nonpolar, so you would only see dispersion. Remember the shapes of this molecule, this was nonpolar, and since it was nonpolar, that's why this is a gas at room temperature and pressure. I don't know what HBr is. That's a good question. I have to look that one up. Is it a liquid or a gas? Hydrogen bromide gas. I'm thinking it's a gas, but I don't know what its boiling point is. I have to look that one up and see, but I would guess that the boiling point of HBr is higher than CH4. Now, SO2, sulfur dioxide, you want to look at its Lewis structure. And when you look at its Lewis structure, you see it has this bent shape. And since it has that bent shape, it's a polar molecule. And you would see dipole, dipole, and you would also see dispersion forces present. So again, this is in a pure, all these were in pure batch, if you will, a bucket of, or a container of HBr or a container of CH4. It wasn't mixtures. Hydrogen bonding is another type of intermolecular force that takes place between a hydrogen that's attached to a nitrogen, oxygen, or a fluorine, and another atom in another molecule. So a lot of times you'll see this as dotted lines, and those dotted lines mean intermolecular hydrogen bonds. And the most common hydrogen bonding that you would see is between water molecules or between ammonia molecules. Now these are gases. That's a gas. Well, actually, you could say these are all gases, but if I cool them down enough, you would get a liquid. But I think I would have to cool ammonia down a little bit more than I would water to get it to crystallize. But you could have a hydrogen bonds in between two different substances, and this would be considered a mixture. Hydrogen bonding, there's that NO and F forms between nitrogens, oxygens, and fluorines, and hydrogens attached to them. So you see you have a partial negative charge here on a water molecule. This guy's called formic acid. And formic acid, these are an O, this is an H, and then this is an H. Here you have partial negative and partial positive. And then you also have lone pairs on that water molecule. So you would get a hydrogen bond in between those two. Now the hydrogen bond is a special dipole-dipole because it is so strong. So your book shows this graph of boiling point versus period in the periodic table. And as you get heavier and heavier, your boiling point increases. That's due to molar mass, and that makes sense. But then sometimes you have these guys that are a little bit out of the trend. I mean, you'd think you'd see something down here from each one of these, but they don't. They're abnormally high, and that's where that hydrogen bonding definition comes in. And this is a little video that I made. I don't know if I can show it, but there's hydrogen bonds in here in between each of the water molecules. You can see them there. And so in a whole grouping of liquid water, they're hydrogen bonded. Now, this is a liquid, so those are going to break and reform. And of course, when they form completely, then they would freeze. And then you would get frozen water, and those hydrogen bonds would remain in place. So that is the end of kind of just we're going over the intermolecular forces of liquids and solids for sections 1 and 2 in chapter 11. So go in and look at your fun sheet. It's kind of an at-home thing where you take some sugar, you take some salt, and you just look at it dissolve yourself. And do it slowly. You can heat it up or you can cool it down. But either way, you should be able to see when you put a sugar in water or salt in water, you'd have some salt, and then you'd have some water. And if you don't disturb it, you'll start to see a layer. And that layer is not going to be easy to see, but just because of the fact that it's colorless. But you can see the differences in density. And you see it looks like almost oily, but it's not necessarily oily. It's dissolving. And so you get a different density in that concentrated salt solution above the solid salt, if you're doing a solid here. And it's going into the aqueous phase. So, of course, if you shake it, you're not going to see that, and it'll disappear, and that means that, when it completely dissolves. But if it doesn't completely dissolve, then you can, and you just don't disturb it, you can see that. So that's in your fun sheet talking about that, as well as dissolving carbon dioxide in water and how that works. So give it a shot at your fun sheet, and when you're finished with that, put it into the assignment.